Okay, and time to kick off the next session where we have Conal talking about timely computations.
All right, thank you, Patrick. Thanks for coming. There's a simple question at the heart of my talk, which is what is a digital circuit? Or what is physical computation? We're used to thinking about computation abstractly, but kind of what gives computation its essence is not just the abstract mathematics that it computes, but what makes it computation rather than math, which is the physics of computation, which is it's a physical process. Information is physical, computation is physical. So what happens when we think about specifically and clearly the physicality of computation? Now, I'm guessing that you have been doing computation for a long time and gotten used to what, in retrospect and on further reflection, is kind of an odd aspect of digital computation. An aspect of computers, which is what they are and what we do with them or why we use them are very, very different things. Okay? So a computer is an electronic circuit. It's a physical thing, and it transforms analog signals. Now, you may think we don't use analog computers anymore. That's something we used to do a long time ago, like in the 30s, and we don't do it anymore. But no, of course we use analog computers because computers are made out of the universe, and the universe is analog. Okay? So computation, physically, is an analog thing. It's a physical analog thing. Now, calculation is usually, not always, but is usually about discrete rather than continuous quantities. So it's more of a digital kind of a notion. And rather than being physical, it's mathematical. Okay? So, an actual physical implementation, physical manifestation of computation is continuous, but what we use it for is discrete. Okay? And one is physical and the other is mathematical. So in what sense could we possibly go around talking about correctly computing when the things that we're doing with computers are so different from their very nature? So that's the question. And another way to ask this question is, what is a digital circuit? So I just said there's no such thing, and yet we use this notion of digital circuit in a really, really important way. Okay. So it's a question. What do we want out of the answer to the question? In other words, what are the kind of properties of a good answer? And these are my preferences. I want a good definition. I want the definition to be clear, so I really kind of know what I'm talking about. So the less fuzzy it is, the better. I want it to be simple. Why should the question be simple? Because the question cannot be verified objectively. Right? If I have a question and I answer it, I verify the answer against the question. But how do I know that I've got the right question? Another way to express that point is once I have an answer, how do I know how to apply the answer? In other words, in what circumstances is it correct? And we do that with our brains. We can do everything else computationally, but to verify a question, we need to use our brains, and that's why it has to be simple. And so, for instance, for me, it's not going to be operational. It's not going to be linguistic, because both of those features fight against simplicity of the question itself. It's going to be simple, denotational, mathematical. Now, also, it needs to be useful. I mean, it doesn't have to be useful if we're pure mathematicians, but I want it to be useful, and I'm guessing most of you do too. Useful means we get some insight out of it that we can solve problems with. We can do things we care about. And I would say formal. Now, formal is a pretty kind of a strict, demanding sort of discipline. But the idea of formality is that it can be machine checked. It's completely unambiguous. We don't have to rely on our diligence, which we're not very good at, to make sure that there are no mistakes slip by. And then constructive. Constructive is that I want to get some insights out of it that I can apply. So it's very much like the useful. And finally, compositional. And I think we're here in part because we love compositionality. But the reason for compositionality is that our brains are limited, right? And we want to be able to build things that are much more sophisticated than we can understand in their entirety. So we build them in pieces. And if we care about correctness, then we're going to approach correctness in pieces. Okay, we're not going to build complicated things and then try to figure out what they're supposed to do and then prove that they're correct. That's a non-compositional approach, and it's too difficult for primates. Okay, all right. So those are my qualities of a definition I'm looking for. And this is my definition of a digital circuit. A digital circuit is an analog circuit that's used in a disciplined way. Okay, so it's not a physical thing. It's a disciplined use of a physical thing. So a digital circuit is an analog circuit that respects discrete meanings. Okay, so what I mean is digital circuits are really going to have continuous flows of, like voltages, some continuous thing coming in, but we're going to interpret that continuous information discretely. So extract, finite information like bits, something like that, out of it. And if we call that the meaning of the signal, now I don't mean it's the meaning of the signal, it's how we choose to interpret the signal. Okay? We want it to be the case that if you put two signals into this circuit, and those signals differ a little bit, but they don't differ in their discrete interpretations, all right? Then the outputs can differ, but not in their discrete interpretations, okay? Okay, so that means that that analog circuit is respecting the discrete interpretation. If that is, if two analog signals coming in are equivalent in the sense of how we interpret it, then the outputs will be not equal but equivalent. All right, so that's the kind of framing, basic framing. And as I said, compositionality is centrally important. It's really the superpower that we use over and over to solve any problem. And of course, correctness. Right? We don't want to just compute, we want to compute something in particular. We don't want to just do random fluctuations of electrical signals or bits. All right. So I want to talk about compositionally correct computing. Then I'll come back to digital computation. So I want to start with just computing. All right, not correct, not compositional, just computing. So this is a picture of computing. Computing is we've got some function f1. That's going to be, in the case we're talking about, that's going to be a circuit itself. It's going to be a function that transforms continuous signals. Okay, so it's got some information coming in, rho 1, information going out, sigma 1. Okay, and it's the transformation. That's what I'm calling operation, or you call that implementation. But that's not correct. That's just something going on. We don't have a way to talk about whether it's correct because we need to compare it to something. So we move up from computing to correct computing. This is my picture of correct computing. In addition to the operation or the implementation or the physics, you might say, we have its intention, which I'm going to call its denotation or its meaning. Okay? Whereas the operation is chosen for its physicality, right? Something that can be computed in this universe, so we can look at it and learn from it. Okay? And maybe computed efficiently, inexpensively. I want its meaning, the kind of the purpose or the intent of it, to be optimized in a different sense. It doesn't have to be physical, it doesn't have to be computable, but it needs to be mathematically well-defined and simple, so it's amenable to precise reasoning. And I don't just mean you can reason about it, but it's friendly to reasoning. Okay. Then we need to relate somehow the thing that is implemented to its motivation, the motivation for implementing it. Okay? And that's the relationship here, the horizontal arrows. So if rho 1 is maybe a bunch of wires or a bunch of continuous signals, then rho 2 is its interpretation via h, that first vertical arrow. That's going to be the function that extracts information. Okay? And for us, that'll be something like bits. Got all this continuous stuff, we're going to extract some finite number of bits out of there. And maybe even interpret those bits as something like a number or a tree, or something like that. Okay, so we know how we need to know how the input, the kind of physical input, is going to be interpreted as mathematical input, and how the physical output gets interpreted as mathematical output. That's H and K. Okay, and then we need a consistency requirement, and that's implied by the little curvy arrow in the middle, which means that this diagram commutes. In other words, if we start with a physical input rho 1 and we pass it through the physical circuit, get sigma 1, and then we interpret it as a kind of mathematical or say discrete meaning, that needs to be the same as if we took rho 1 and interpreted it, the input, and then passed it through the mathematical function. Okay? That's what correctness means. Now that's how I'm defining correctness. So it's the commutativity of this diagram, saying those two paths are equal. Okay? So that's correct computing. What about compositionally correct computing? Okay. So the idea is, if we know what correct computing is, okay, and we want to do ambitious things correctly, right, then we're going to need to compose them. And if we want to be able to succeed, we need the correctness at every step, instead of postponing until the very end and having a gargantuan task. Okay? So I want to know, how do we compose these correct things to make other correct things? Okay? So that's where we get compositionally correct computing. And what I'm suggesting is that you take this diagram and you can see it in parts. So I showed you one kind of parsing of it, which is these three layers, right? The three horizontal layers, operation, denotation, extraction in the middle. But there's another way to slice it, okay, orthogonally, which is to say on the left we have some notion of the input. Now we really have two things or three things about the input. What's the physical input, what's the conceptual input, and how does the physical relate to the conceptual? That's H. Okay? Or you could just say it's H, right? And its domain and codomain are a part of it. All right? So we know about the input and we know about the output. its physical manifestation, its conceptual intent, and the relationship between them. Okay? So that's a kind of domain and codomain of correct computing. Okay. Now, what about a morphism, or what about the kind of functionality, or the computation itself? Well, that's going to be this middle row, this middle column. So it's going to have the implementation and its purpose, its meaning, okay, and a proof, and that's what the curvy arrow is. The proof that in fact this relationship holds, this commutation. Okay. Now, why do I call this compositional? It's because these things compose in a really nice way, and I'm going to show you what that looks like. So we have these packages of correct computation: intent, implementation, proof of correctness, including the extraction. Okay. Now, how do we combine them so that we can build bigger correct things from smaller correct things? Well, one very useful way to combine subcomputations is put them in sequence. So if we have these two correct computations, the one on the left and one on the right, and the one on the left feeds into the one on the right, in other words, the output matches the input. Now, when I say the output, I'm including both outputs: physical, or say implementation, conceptual, and interpretation. Okay? So when those line up, we can compose these correct computations into a single correct computation. Okay? What happens? The implementations get composed sequentially, the meanings get composed sequentially, and the proofs get combined in a standard way. There's like, if you try this with only one right thing that could possibly work, and it does indeed work. Okay? So you can combine the proofs in a clever sort of way. All right? So sequential composition is just one way that we build up computations. Another main way is parallel composition. So here we have two correct computations, and now the domains and codomains are unrelated to each other. They're completely independent. Unlike the previous one, these are unrelated to each other. Okay? And we can combine them in parallel. So what do we do when we combine them in parallel? Well, the inputs get paired in the physical manifestation and in the conceptual motivation. The outputs get paired, again, in the same way. And then the functionality, both the implementation and the mathematical intent, the mathematical function that motivates the implementation, gets not exactly paired up, but put in parallel. That's this cross operator. So it's like a pure parallel composition. It just means you run two computations in parallel. They consume a pair. You divvy up that pair to each computation. You take the two results, put them back into a pair. That's just a common operation here. Now, what I've shown you are the basic building blocks, not all of them, but most of them, the basic building blocks of what's called Cartesian categories, which is kind of the basic building blocks, or some of the basic building blocks of computation in general. And not just computable functions, but differentiable functions, linear functions, polynomial functions, incremental computation, all kinds of things can be looked at in terms of this vocabulary. And they have very nice properties. And they're related to the type lambda calculus in a very kind of simple, universal sort of way. Okay. Well, the story's a little bit more involved in this, which is I don't want to just have computations here that are all like mathematical functions. I want my circuits to be more real than that, than just the mathematical functions that they implement. Because why? Because I want to be able to like build them. I want to be able to synthesize, maybe like Verilog and build a chip, that kind of thing. I need some sort of more analyzability that I can get of mathematical functions. So we introduce representations. And the idea is that we have two mappings from representations. That's the capital Ph's. Okay. We have one at the implementation and one in the meaning layer. And what that does is it's a subtle sort of shift, but it means that the data in this diagram, or the data in the representation, is not just the meanings, but it's the things that mean what the meanings are. In other words, it's like the actual circuit, not just its mathematical interpretation. Okay. So it's a bit of a subtle point. You can read the paper. Okay. This whole composability story works out with this extra bit of very kind of practically important layer. And it works out when these fees, these interpretations, distribute over the kind of structure of these operations. So it really relies on phi of f, phi of g composed phi of f being equal to phi of g composed f. Okay? So that's its homomorphism property. For categories, that's called a functor, okay? Or a Cartesian functor. So that distributed property. So that's what you need. You need a functor. All right, so that's the basics. Now, what does that have to do with the question I started asking is, this is how I want to approach building sophisticated, very efficient physical computation and have it be guaranteed correct and have it be sort of reasonably easy to build at every step. Don't want to make it hard, want to make it easy. All right. So now I want to ground in a fairly concrete example. Okay, and the example is a classic, which is a full adder. So a full adder you can think of as adding 3 bits. Okay, another way to think of a full adder is to add 2 bits and a carry-in bit. Right? Now the result can be, well, the result is going to be up to 2. Oh, I need 2 bits. Sorry, it's going to be up to 3. So I need 2 bits for that. All right, so that's why there are 3 inputs, 1 input per bit, or you could say 1 input per wire. The wire is the physical view. The bit is the sort of interpretation view. Okay, and 2 outputs, one per bit. Okay, so now here's a question. I want to build a correct implementation of this. I want to build a correct something that embodies the digital semantics, okay, of adding numbers. But remember, my substrate isn't digital because reality is analog. Okay, so to know that I've implemented physically this computation, I have to take into account the physicality of computation. And one of the implications is that computation takes time. Right? It takes time to compute and it takes time to move information. All right. So understanding correctness relies on understanding timing. Okay, when we embrace the physicality. One reason to embrace the physicality, I didn't say so, is because you can get a heck of a lot of performance gain if you do that. It's wonderful that programming languages, especially functional languages, especially genuinely functional or denotative languages, take the physicality, the timing, for instance, out of the picture. But there's a huge cost in performance. There's a huge cost in time and in power consumption. Okay, so if we take timing into account, then there's a natural question arises, which is when should you look at these wires? All right, because remember that's the interpretation. We have these continuous signals and we're pulling out bits. How do you get the bits? By looking at the wires at certain times. So how do you know when to look at the wires? Well, that's tricky. Anything that's tricky should be approached compositionally. All right, so. And I want to know what's a clear question to ask. So here's a clear question to ask, which is if I know when to look at the inputs, okay, then when should I look at the outputs such that this correctness property holds? Okay, because remember, when is the interpretations. Right? That's how we get our digital interpretations. So that's a question. If I know when to look at if I know when I'm going to look at the inputs, then when should I look at the outputs so that the result, the bits I pull out, accurately reflect the mathematical function that's motivating the construction of the circuit. Okay. So, turns out there's some subtlety in this question. So what notion of when is going to be useful and tractable logically? So one question is, do we have a when for the whole circuit? In other words, one particular time. This is the time at which you look at all inputs. Okay, given that, then I figure out the time in which you look at all outputs. Well, that's a simple answer, but it turns out if you do that, you lose a lot of precision. Okay? In other words, the timing prediction would be much worse than if you looked at it in a fine-grained way, rather than a coarse-grained way. Also, it breaks some compositionality. Okay? So per bit timing, so a time per bit, has a big payoff. Okay? But there's another question. So then you might say, okay, so suppose I know for each bit when to look at it, what moment to look at it. And then I can ask the question, at what moment will the outputs be correct? Well, turns out, in most cases, no moments at all. Okay? And why is that? The reason for that is that pathways through a circuit have different lengths. It takes different amounts of time for information to pass through. So here I'm looking at 2 of these. We take one of these inputs, say I1, and we're going to look to see the output of this NOR gate. Okay? NAND, XOR, not NOR. Okay? Well, let's look at these. So NOR has 2 inputs. Let's trace back how much time passes between a single input bit and this NOR. Well, this path has 2 gates on it. Right? This path has 1, 2, 3 gates on it. This path is going to take longer. So it's going to take longer for one of those paths to propagate information. So if I know exactly when I1 is valid, then NOR will get one valid input at one time and the other valid input at another time, and it will never get 2 valid inputs at the same time. And assuming that's the same propagation delay from each input to the output of NOR, it will never give a correct answer. Now, I don't mean that it never will. We can never guarantee that it will give a correct answer. It might just by luck give a correct answer. But we want to know, when can I guarantee? Because that's when it's guaranteed to be correct. So what can we possibly do about that? Well, we can change the question. And instead of talking about at what moment the inputs will be valid and what moment we should look at the outputs, we can say, how about over an interval? Suppose you could give me an interval of time over which the inputs are guaranteed to be valid, okay? As long as that interval is long enough, then this NOR will receive valid inputs at the same time. And that time will be the intersections of when kind of the validity of the information coming into one input or the other input. They're going to be off, but if the duration of the original input is big enough, then that intersection will be non-empty. And that intersection will be exactly when we'll have valid information coming out. Okay? So instead of using a single time, we're going to use a time per bit. Instead of treating time as a moment, we're going to treat time as intervals. And what we mean by an interval is that it's valid over the entire region. Okay. All right. So this slide is like a very simplistic way to think about an actual analog computation. So analog circuits always have meanings if you're not trying to interpret them digitally, right? They just transform continuous flows of information. Here's a very simple way, it's in the paper, of saying what that is. It's not a realistic way, but it's kind of a very simple way. All right. But the shift from analog to digital, the kind of main idea there is, as I said, we want to identify intervals, but those intervals aren't just intervals. Something happens, something is true during those intervals. And what's true is stability, what I'm calling stability. And what stability is just that the signal holds a particular value during that interval. Now, really, the signal is a continuous voltage, and it doesn't hold a value. It wavers, but it wavers near a particular, like every voltage level in that interval has the same interpretation. So I've simplified it and kind of simplified away the tiny waverings here, but it's not hard to fix that. So the definition of stability, a signal is stable if there's some interval. Okay, there exists an interval. Oh, there's an Agda, by the way. There's an interval x hat and some value, static value, a boolean value, x, such that the signal holds that value during the interval. In other words, for all times in the interval, the signal at time t is equal to x. Okay? So that's what I mean by stability. Okay? So the idea is, let's not talk about arbitrary signals we're passing through. Let's talk about signals that have this stability. And it's a constructive notion of stability, which is not only, do we know that these intervals of time and Boolean values exist, but the proofs contain the specifics information. So the fact that I'm working in constructive logic means there's a little bit more than meets the eye here, which is that there's computational content. So we actually have these intervals and bits to work with. Okay? Now, this is about one bit. What about multiple bits, right? Multiple wires? Well, we're going to tuple up these things. In other words, for every bit in a tuple, we'll have the signal, we'll have the interval of time, we'll have the bit value. Now, in the end, what actually gets run is only an analog computation, and then what the user has to know is only the timing, so they know when to look. Okay, and this sort of pattern about values that have a certain property, like stability, and functions that preserve that property. Okay, that's this kind of general pattern that could be described in a very general way and reused. So that's what I do, and it's described in the paper. Okay. Now we can talk about stable gates. What is a stable gate? It's a gate that has a property of preserving stability. Okay. So this is in the paper. The important thing I wanted to call out here. So we have this notion of stability, and then a stable logic. In other words, like digital gates. Digital gates, remember, is a physical gate used in a disciplined way. Can be easily built out of these standard kind of building blocks. These deltas are the delays, or the propagation delays. All right. Now, what I skipped over real fast is how timing is computed. And there's just these three operations. So remember, every gate is going to consume and produce some number of signals. In this case, 0, 1, or 2. All right. And so the timing computations need to work with no signals. That's pretty trivial. One signal, you just delay it by a certain value, or two signals. Two signals, you delay each and then intersect the results. So remember, they both have to be valid to get a valid input. Okay. So the basic building blocks of these timing computations are the universal interval, minus infinity to infinity. Okay. This thing I'm calling star for convolution, okay, which is also called Minkowski sum in this case. That's the idea of you have two intervals and you add them, which means you form the interval, which is like sums of values, one from one interval, one from the other. It's more generally a set notion. Okay. turns out to be a special case of convolution. And then the third one is this like intersection operator. Those three operators turn out to be, to form a semiring. There's a fourth one, which is offsetting by nothing, right? Offsetting by 0, right? So that's the fourth one, the singleton 0 interval. So this basic vocabulary forms a semiring. Well, that's kind of interesting, but so what? So what is that timing is linear in this semiring? Okay, so all of the timing computations, if you think in terms of this semiring, they turn out to be linear. And that's a huge win for a variety of reasons. One is that it means that instead of representing this timing as a function from intervals to intervals, we can represent linear functions in a data sort of a way, which is what matrices are about. If we do that, it also turns out that timing analysis, I believe, is really essentially automatic differentiation. That's what automatic differentiation is doing as well. It's computing linear approximations. And then in this sense, statically timed hardware is affine. What I mean by affine is a function with a constant derivative. All right. So now, if we look at our full adder example, and we crank it through this compositional analysis where we represent the timing as linear transformation and then really as matrices, we get out this sort of result. So this is a matrix. It may be a little hard to recognize, but the importance of being a matrix is you can look inside. There's no hidden information. That information tells you the timing properties of the circuit. Okay? If you don't like the timing properties of the circuit, find a circuit whose timing properties you like. Okay. All right. So that's basically it. There's a bunch of potential improvements, further work, some's in progress, some isn't, that's in the paper. But I think that's a good time to stop and take questions.
Yes, usual microphones, and there is a chat, which so far is empty, I think.
Thanks for the talk. Is this on?
Not on.
No?
I don't think so. Is that one?
Okay, this is on, I guess. Okay.
The recording won't hear you if it's not on, I think.
Okay. Thanks for the talk.
I'll
It's
repeat the
great.
question. Yeah.
I was curious, when dealing with, say, a signal that's a product of multiple bits,
Yeah.
and you have the time interval for stability,
Yep.
do those different bits have different and potentially related stable intervals, or is the encodings you've looked at just have a single stable interval in time for the product of those bits?
Thank you. Yeah. Thanks, Gilbert. So the question is, I think, correct me if I'm wrong, please. I think the question is, when we have these multiple bits, and I'm talking about the intervals, they each get an interval. Are the intervals the same? Are they really getting different? Are they really having the freedom of having multiple intervals? And there's absolutely yes, and it's incredibly important. Because, like, if you look at, for instance, a ripple adder kind of circuit, right, you don't need the inputs all at the same time. They're not going to be consumed at the same time. You don't need them at the same time. So if you insist on them being at the same time, you'll get badly timed circuits. Yeah. Yeah. So precision, performance.
Thanks, Conal. So all of this sort of suggests that, well, feedback is a very common property in circuits.
Yep.
I'm having a hard time seeing, how can you make this work? How do you interpret the feedback?
Thanks. Yeah, so that's the first bullet here. Yeah, so what I showed you is this kind of simple part of the story, all right? Now, actual circuits have feedback. Feedback is what gives you temporality. It's what you lay out. It's what allows us to lay out computation in time as well as space, all right? Okay, so the definition of stable I gave you is this kind of a simplification. It's you identify a single interval of time. All right, so that's how you get one bit out of a wire. Well, wires can hold a lot more than one bit. So what you need to do is to take that definition, generalize it in a fairly simple way, which says you don't have one interval of time, you have a bunch of intervals of time. All right, you have like a tuple or a tri or a vector or whatever you want, and the same shape, of bits, right? And then a proof that for each of those times, the signal holds the value over that time. Yeah. So that's kind of the first step. The next step then is to look at it exactly like how do you want to formulate cyclic circuits, or you could say recursive. And a nice way to do that in the same kind of general vocabulary is what's called a monoidal trace, It's a kind of a feedback. It's the way you talk about something like recursion or cycles in categories, okay? And so that's something that I've kind of worked out on paper, but is definitely not in this paper. Yeah. So yeah. So anyway, it's a matter of looking at the inputs, looking at the outputs, and then first of all, you got to make sure that loop is well founded. Okay. The well founded of that loop is why hardware designers usually put registers, right, in their loops. Yeah. But the essential thing is not registers and loops. It's a well foundedness of traces. Thank you.
I'll just try to insert one question from the chat, Edwin Turek. It's a little long, but I'll see if I can say the actual sentence with a question mark. Can your approach be used to implement efficient and correct asynchronous circuits without the usual metastability problems that affect clock domain crossings?
Thank you. Yeah, I'm really excited about that question. I'm not just getting it, but I've been excited about that question. So I really tried in this paper and in this work not to assume global synchrony, not to assume synchrony at all. So what I described to you doesn't assume synchrony. There's no clocks in this description. So it can be refined to talk about clocks, and with the cycle story, that's where clocks come in right there. But I don't think it needs. I think it applies more broadly, and that's one of the reasons I pointed out the connection with automatic differentiation. Is that in more broad computations, the timing is data dependent. Okay? And as in automatic differentiation, that's like saying the derivative is input dependent. That's just saying it's not an affine function. It's an interesting, wiggly kind of a function. So I think this framework does support it, and I haven't tried it. Thanks.
Okay, one last question.
Satnam Singh, Grok, where we make silicon chips, and I spend a lot of my time looking at timing reports. But when I think about both combinational circuits and sequential circuits, my model is set up and hold, and all the timing violations that come from that. Even for a combinational circuit, they'll have a register somewhere, right? And I'll have to worry about set up and hold for it. So I'm not thinking in terms of intervals. I'm thinking of how many seconds have these signals together been stable to work out what the output's going to be. So does what you've described, does it map into the normal world of timing analysis for hardware, which is all based on set up and hold?
Yeah. Well, I think it does, and I think that's exactly what motivated this work. Was I was working for a different hardware company, and I went around asking hardware engineers, like help me fill in my gaps here because I'm a software guy. What on earth is timing analysis? Yeah, and it was really from those questions, and it was like almost nobody gave me any helpful answers. It was more like, now I struggle with this expensive, industry tool or something. But I think there's the setup and hold analysis that they do. All right, in actual hardware timing. I think setup and hold analysis is what I'm talking about. I'm just talking about it in a neater way. So one of them is the lower bound of the interval, the other one's the upper bound of the interval. One of them you max, the other one you min, but in both cases they mean intersection of intervals. You could talk about some intervals of semi-infinite and you're intersecting. Yeah. The others are semi-infinite the other way and you're intersecting.
Yeah, but you mentioned this in the answer to the previous question. I guess what's been missing for me is the global clock, right? Because all these signals are relative to this clock.
Yeah. Well, that's one kind of computing, and I really wanted to tell a story that's more general than like globally synchronous computing. Yeah. And now, of course, a sequel is show that this story really explains globally synchronous computing and multi-clock domains and what's called asynchronous computing. It might be better called, like very locally synchronous computing or dynamically synchronous.
Thanks, Conal, for a great work.
Anyway, thanks.
Okay, thanks.
All right.
Well, I have to move on, so thank the speaker again.
Thank you very much.